In this video, we're going to look at a series of reactions. So I'm going to show you a demonstration where I add 6 molar hydrochloric acid to copper, iron, magnesium, and zinc. In this demonstration, we're going to look at a series of reactions. I'm going to put in these test tubes. In the first one, it's going to be a piece of copper. In the second one, I'm putting some iron. It's actually a little piece of wool. And you've probably seen that if your mom has pillow pads or something like that. In the third test, I'm putting a little piece of magnesium. And in the fourth, I'm putting a little piece of zinc. And I'm going to add some 6 molar hydrochloric acid to each of those so we can see what kind of a reaction it is. So first I'll add it to copper. So we're going to look at evidences of chemical reaction, things like color change, gas production. Don't really see anything happening there. Let's try iron now. See what you see there. You put a little bit more in so it'll cover it. Well, there's not a whole lot going on there either. Okay, well, we'll watch these for a minute and then come back and see if anything changes. So in the next one, look at magnesium. Now you've seen magnesium before. We've burned it a few times, and that one's always a fun one to do. So let's see what happens when we put into hydrochloric acid. So obviously at the very beginning, it went ahead and started bubbling. And you could see that a gas was being produced in the bubbles, and now you can see that the magnesium is gone. It has basically dissolved. And then we're going to look at zinc and hydrochloric acid as well. Now here you can see the zinc is also bubbling and producing some gas. So let's continue to watch and see what happens there. You can see a little gas being produced. If you feel it's a little bit warm, if you feel the tube on the side. Right, so let's go back and look at our test tubes here. We've got our copper, and you can see if you look, nothing is really happening there. Okay, you can see the piece of copper still sitting there on the bottom. Now, the iron, you may notice that the color of it has a yellow. So that is actually beginning to react, and sometimes you can see little bubbles forming in the little wires of the steel wool. So you may be able to see some really tiny bubbles starting to form there. So there is a gas being formed, but it's just very small amounts at this point. Now with the magnesium, of course, it completely dissolved. And the zinc also made a gas and has reacted pretty strongly. So let's talk about what that means. So the first thing we need to do when we're trying to figure out a reaction is determine what type of reaction it is. So if you look at this reaction, let's write the one for copper. You can see that we added copper, just Cu, and copper we know is a solid. Most metals are solids at room temperature. And then we added that to hydrochloric acid. Anything that has a molarity for us is an aqueous solution. And when we put those things together, we saw that there was no reaction. So let's look at what type we think it would have been. So looking at this, we've got one element and one 2-part compound. So think about that for just a second and see which type you think it might be. Hopefully you said that this looked like a single replacement reaction. So let's go ahead and look at the rest of these because there were reactions with the other 3 metals. All right, so for our first one, we'll do iron. Again, iron's a metal, it was a solid, plus HCl. And HCl again is always going to be AQ for us since it was a solution. And in this case, I would have to tell you what the charge on the iron would be in order for you to write this reaction. In this reaction, the iron replaces the hydrogen. So remember that iron forms a positive ion. Hydrogen is a positive ion. And so it needs to replace the positive ion in the compound. So iron would have a +3 charge, and I would have to tell you that. In this case, it makes iron 3 chloride. And then what would be left would be hydrogen by itself. It's going to replace hydrogen, so it's going to kick off hydrogen by itself. So iron 3 chloride, iron has a 3+ charge. Chloride is a 1-, so it's going to be FeCl3. And then hydrogen, we know, was a gas, and hopefully you recognize that it's covalent and is likely to be a gas at room temperature. So next, let's look at balancing this. We've got 3 chlorides. All right, so we know that hydrogen was the gas produced. Iron 3 chloride, we need to decide the symbol for that. So look at your rules for solubility and determine whether or not it's soluble in water. You should see that it is, so that is AQ. And then we'll go ahead and write these other reactions for magnesium. So magnesium is a solid plus HCl, AQ. And again, magnesium will replace hydrogen to make magnesium chloride. We already know the charge on magnesium, it's a +2, so it's going to make MgCl2, and again, it's going to make hydrogen gas. All right, and then the last one would be zinc. Again, it's a solid plus HCl, AQ. And then that would make zinc chloride. Zinc also has a +2 charge, so it would be ZnCl2, and then H2 gas. Remember to check your solubility rules, and hopefully you saw that magnesium chloride is aqueous and zinc chloride is aqueous. All right, so think back to what we saw in the demonstrations. Which of those metals was the most active? Thinking about which one reacted the most strongly. Hopefully you said magnesium, because when that magnesium hit the acid, it just disappeared. It just completely went away. The next most active metal would be the zinc. So it bubbled quite a bit, but it was not not as strong of a reaction as the magnesium. The next most active metal was the iron. It turned a little bit yellow in the solution. There were some little bubbles of hydrogen. They were difficult to see in the video, but there were some little bubbles of hydrogen. And then the copper did not react at all. So that would be the least active. So let's put those in order. So hydrogen is produced. We said the most active metal was magnesium. The least active was copper. And that's the order of the reactivity. And what we have is a nice reference table what we have is a nice list in our reference table so that we can use that to predict whether or not reactions will occur. So instead of having to actually do the reaction with copper, we can tell that that reaction would not take place. So let's look at this. This is called the metal activity series. The most active elements are at the top, and they will replace anything below them in a compound. So you can see magnesium is here, hydrogen is here. Hydrogen is the only nonmetal on here. But magnesium will replace hydrogen. It would also replace any of these other metals in a compound. And those elements are more stable when they're in compounds. We've talked about strontium, calcium, sodium, especially those group 1 metals and how reactive they are. So you can see those group 1 and group 2 metals are right up at the top.
And then you can see that the least active elements are at the bottom. When you think about, like they call copper and gold and silver, they call those coinage metals. You don't want coins or jewelry that are made out of things that would react with your skin, the sweat or anything from your skin. So copper, silver, gold, platinum, things that we make jewelry and coins from are at the bottom. And they're more stable by themselves than they are in a compound. And so when an element's already in its most stable position, it won't react. So you can see here copper is below hydrogen, and so it won't react to replace hydrogen in a compound like hydrogen chloride. There's also another activity series, and you will probably want to put a nice big line in your reference table between them. The top series is for halogens because there are halogen replacement reactions. The bottom series is just for metals. All right, let's go ahead and take a look at a few examples so that you know how to do these. So here are your normal instructions. Here's your problem. So let's go ahead and write that together. So we've got aluminum metal, so aluminum, which we know is a solid. And then it's added to a solution of copper 2 sulfate. So copper has a 2+ charge, sulfate has a 2-, so it's going to be CuSO4, and that's going to be AQ. All right, so we know that this is a single replacement because it's one element and then a 2-part compound. And that we have to look at the activity series to determine whether aluminum will replace copper in a compound. So let's take a look at that. So looking here, you can see that aluminum is right here and copper is way down here at the bottom. So aluminum will replace copper because copper is below it. So the metal that's by itself needs to be above the metal that's in the compound. So let's look at that and figure out what the products would be. All right, so if aluminum replaces copper in that compound, our new product will be aluminum sulfate. And remember that it will replace copper, so copper will get kicked off by itself. So it'll just be copper here by itself. Remember that aluminum is a +3 and sulfate is a 2-, so that's going to be Al2 and then SO4. We'll need 3 of those to make that a neutral compound. And then copper by itself. Now, first let's figure out the symbols. If it's a solution, we need to check for solubility. Hopefully you guys recognize that copper would not be soluble in water. The Statue of Liberty is made of copper, so it would not be standing if it were soluble in water. So copper would be a solid, so it would precipitate out of this reaction. And then aluminum sulfate, you want to look that up in your solubility rules. And that would be AQ. So make sure you're looking at the rules for this. And then we would want to go ahead and balance our equation. So remember to start with your polyatomic ions. So sulfate is the same on both sides. So I'm going to put a 3 here. And that gives us 3 sulfates, 3 copper. So I'm going to put a 3 in front of the copper. And then we need a 2 in front of the aluminum to make that balance. Let's try another one. In this case, we have magnesium metal added to a solution of potassium chloride. So let's write the left side of that equation. So magnesium metal is Mg, and that would be a solid. And the potassium chloride, potassium is a 1+, chloride is a 1-, so it would be KCl. And it's a solution, so its symbol would be AQ. Now, remember that for all single replacement reactions, we need to check to determine whether or not magnesium will replace potassium on the activity series. So take a look, find magnesium and find calcium on the activity series. You can see that magnesium is up in the upper part of the activity series, but if you look, potassium is even higher up. So magnesium will not replace calcium. So for this one, we would put no reaction. At that point, if you are sure it is not a reaction, you will go ahead and just put no reaction. You don't need to put the products in balance. But I will tell you on tests that when you write no reaction, if it is a reaction and you haven't put anything else, I'll start marking off for whatever isn't there. So my suggestion would be, if you're not 100% sure that it's a no reaction, go ahead and write the products, put the symbols and balance it, because if you put no reaction and it's not a no reaction, you'll lose points for saying that it's a no reaction, but then you'll lose additional points because I'll grade what's left. All right, let's take a look at another one. All right, so go ahead and write the left-hand side of this equation, pause the video, and then start it and make sure that you have got it figured out. And take a look at the activity series and see if you can figure out what would happen with this one. All right, so let's go ahead and set this up. Lithium metal, so it would be lithium, which is a solid, is added to water. Now water, believe it or not an aqueous solution. Water is a liquid, okay? Most covalent compounds are liquids or gases at room temperature, and water, while it is part of an aqueous solution, it's the liquid part, the solvent in the solution. So water is always a liquid. All right, so what you want to do is look at that activity series and determine the position of lithium. Now with water, water does not have a metal in it. So what we want to look at is the little arrows on the series. So let me show you that. So looking on the activity series, we have the lithium metal, which is up at the top. And then water, you can see these little arrows. Lithium will replace hydrogen from cold water. So all of these metals at the top that are next to this arrow, lithium through calcium, will replace the hydrogen from cold water. And then actually even sodium, I think, will, depending on the temperature. And then lithium down through iron will replace the hydrogen from steam. And then you can see all the way down through hydrogen, it'll replace the hydrogen from acid. So you just want to pay a little bit of attention to those arrows. That's what that's for. And let's go ahead and finish writing that reaction, because lithium is above hydrogen and it's over here in this area where it will replace the hydrogen from the cold water. All right, so if lithium replaces a hydrogen from water, it only replaces one of the hydrogen atoms. And so it will leave, if one of the atoms leaves the H2O, you'll have an OH left. It makes lithium hydroxide. And if you look on your reference packet, you can see that there is a single replacement reaction, and it shows underneath there the replacement of hydrogen from water. And the metal hydroxide is the product. Remember that lithium has a +1, hydroxide is a -1, so LiOH would be the formula of the compound that's formed. And then when those hydrogen atoms get kicked off, they're going to form hydrogen gas. Remember that hydrogen is diatomic, so we always write it as H2, and we said that this is a gas. There's water here, so we want to check for the solubility of lithium hydroxide. And hopefully you can see that lithium hydroxide is AQ. Now, we're not finished yet. We still have to balance this. So if you look, we've got oxygen, the hydrogens and the oxygens the hydrogens are not balanced. So this is one of these where you've got one hydrogen here and two here. And so I'm going to put a 2 in front of the lithium hydroxide, which gives me a total of 4 hydrogens. I'm going to put a 2 in front of the H2O, so that gives me 4 hydrogens and 2 oxygens. So everything is balanced except the lithium. And we can just take care of that by putting a 2 there. Okay, let's try one more. All right, so this talks about chlorine gas being bubbled through a solution of sodium bromide. Now, chlorine is not a metal. We've looked at that metal replacement series, but it's actually a halogen. And so we're going to deal with this other series. So let's go ahead and write this reaction. So chlorine gas, remember diatomic molecules, Brinkelhoff. Brinkelhoff. So chlorine is a diatomic molecule, so it would be Cl2 with a gas. And then it's a solution of sodium bromide. Sodium is a 1 plus, bromine is a 1 minus, so that would be NaBr with a AQ. And then we need to figure out if that will react. So look at your activity series. Now this one is the halogen activity series, the one on top. Let's take a look at that. All right, so the halogen activity series is the top series. So we've got chlorine plus sodium bromide. Thinking about that, chlorine, when it forms an ion, it forms a negative ion. Chlorine usually forms a 1 minus ion. So it is only going to replace bromine in sodium bromide. It can't replace the sodium. It has to replace the negative ion. So we want to use the series the same way. We want to see if chlorine is above bromine, which it is, which means that it will replace bromine in a reaction. So remember that chlorine will replace bromine, not sodium. A halogen will only replace another halogen. A metal will only replace another metal or hydrogen. So if chlorine replaces bromine, the name of our compound is going to be sodium chloride. Hopefully you recognize that as good old table salt. And sodium is a 1 plus, chloride is a 1 minus, so it's going to be NaCl. And then it's going to kick off that bromine. Remember, bromine is a Brinkelhoff, a diatomic molecule, so it's going to be Br2. Now, we need to think about the symbols. So sodium chloride, if you look at your solubility rules, this is a solution. There's water here for it to be dissolved in, so it would be AQ. And then bromine, remember that there are a few elements that are liquids at room temperature. Bromine is one of them, so that's going to be L. And now we just need to go ahead and balance this. We've got 2 bromines so on the right, so I'm going to put a 2 here. And then we've got 2 chlorines and 2 sodiums on the left, so I'm going to put a 2 there. That's it. So what you want to remember for single replacement reactions is that you check the activity series to determine whether or not the reaction will occur. This is different from double replacement, which is where we check for the formation of a precipitate. So for single replacement, always check the series. For double replacement, always check for a precipitate. See you in class.